Curtis.
Hello.
I'm a bit late, so give me a few minutes. I did get your email, but I haven't looked into it yet regarding the homework.
Yeah, I turned it in yesterday.
And repeat that. I think I didn't catch it. It's okay.
Yeah.
Want me to do it this week or just?
I think, yeah, I can have it.
2 weeks, so.
I saw sent out an email. I think I will replace tomorrow's meeting with next week.
Okay, and then, yeah, that's what I didn't know too. I should ask him for the week after Oak Ridge or 2 weeks after, because if we were like switching our meeting day, or we're gonna keep the original schedule.
Yeah.
Yeah, I know, I am.
Yeah, I was gonna have Oak Ridge and then the week after that, a meeting.
Okay.
And then probably like one more meeting.
Before
That'll be the
this
last
season.
one. Sure.
Oh, Dr. Shedrish.
Yes.
This is kind of off topic, but I think in the past, I've heard you reference that, and I've seen that a lot of physics majors will go into finance and work for like on the stock market or something like that.
Mm-hmm.
Do you know what kind of position that would be? Like, what would I look at?
Quant.
What's that?
Quant.
Quant?
I think it's called quantitative analyst.
Okay.
If you want, I have a couple of friends who work there, and one of them especially has said that he'll be interested if I refer to them, but he wanted someone who is fluent in what is this called, stochastic calculus. So if you can take some courses on that, then I can I'll be glad to refer.
Okay, thank you.
Come on. I think it's so are you interested in it? Is that what you said?
I've been getting interested in the stock market lately and looking at like just like technical indicators, and yeah, I mean, it interests me. I think I'd still want to pursue a PhD after graduating, but you know, this is like
That's challenge.
I have some interest in it, so I kind of wanted to explore it a little bit.
Very good. So your homework, Chen. It's on Monday. Is this still visible? Curtis?
Yeah, I can see it.
Okay. Do you want me to change the pen? Just let me know.
All right.
And I think if everything stays as it is, it's an in-class exam. I know there is a holiday in here. Election day is a holiday, right? Is this, are we missing in class?
It's on the third, I think it's
so-
Tuesday.
Yeah, I think it's on.
So it's on Tuesday, right? Oh, yeah, so usually on Tuesday. So we don't, so we will have a class on Wednesday, so it's not missing it. Okay. But I think there is one more holiday, right?
Veterans
Yeah, I think.
The 11th,
Do you know which day it is?
Wednesday, I think it's.
Wednesday. Okay, so then we will miss the class here, but then that's after the exam. So
Is
that's not-
for November 3rd, is there, like, I mean, no class or?
There is, as far as I know, university is closed. I don't know about university, at least
Because I know
teaching is.
I was supposed to have an exam on that day. I just realized that it's election day.
Which course is this?
Don't know.
Probably they are not aware of it, so just mention it, write an email or so.
Yeah, because
I don't
first
think
one
it
we
can-
did in person, so I wasn't sure.
Thermos that night.
Is this Dr. Sivakumar?
Yeah.
So maybe he missed it because this is not a normal thing.
Yeah.
So
Well, I wrote it down a while ago. I can ask him about it.
yeah, so it's not still not very far that you can change it. Yeah. But if it is, you cannot have it down that way, probably, unless it's an online. I also looked up final exam for this course. Remember that these days they announced it after a month or so, the 4th or 5th week. So it's December 11. Check it on your own also. Made mistakes in the past. It's 2:45 to 4:45 p.m. It cannot be in class because the university switches to online mode. After that, the two options I have is to have it online or take home. So there's a good chance that it will be take home unless I have any very strong reasons to do that. It will be a take home examination. Okay. But let me not announce that as a tentative take home. Okay.
But you just mean like as like test one was instead of like submitting something online? Or would,
Tell that again.
like how our first midterm was?
Our first midterm, how was that?
It's like a take home.
Yeah.
Kind of.
Yeah.
It's
So
online format.
Like that. Or
did I do it in the class? Did you guys have to come to the class? No, right? Yeah.
no,
So
that
it
was
was,
the second one. Yeah, the first one you just gave to us, we had like a couple days or something.
yeah, exactly. So it will be available on the course web page, and probably I will make it available a few days before. It's not going to be that it won't be a timed exam in the sense of 1 hour or something, but it will be due at 4:45 p.m. Right. So that will be strict, but if I think I can make it, usually I made it available 1 week before, like right during the exam week, I can make it available. Once it is more than 2 hours, it doesn't matter.
Doesn't be.
Yeah, so you can finish it off early and then you're done with the course. That's also possible. So you can plan it accordingly. But remember, I haven't decided yet. So don't, if you're having travel plans, talk to me. If you would really like to go before Friday, talk to me that whether I've decided about take home. There's a very good chance, 95% chance it will be take home instead of using a camera and other thing to take a course. Unless, why I would decide the other way is that if there is someone who is really on the border and I'm really some sensitive score, then I would really like to take the test which is properly administered. But I don't see that at this stage. But I don't know. So after midterm 3 is a good time to decide this. It's by the time most of the grades will be finalized. So, yeah, is that clear enough? Yeah.
Yeah.
Okay. Okay. We were talking about method of images. It's a very strong method in the sense that if you have a conducting material, so this is a conductor, perfect conductor. A perfect conductor for all purposes, gold and most of the metals that we know around are reasonably perfect conductors. And this is vacuum, which is basically atmosphere. And we said if you have a positive charge here, it is equivalent to forget the conductor, delete the conductor altogether, and replace it with a negative charge. And that's what it behaves like. The force is pretty much like Q1, Q2, and its image is actually negative Q. If this was positive charge, then it's negatively charged. If it was a negatively charged, it is oppositely charged. If this is distance A, that's also distance A. Very much like optics, right? If you're thinking of an image of yourself in a mirror, you can ask where is the image located? It is exactly the same distance as you are away from the mirror. It is not. I mean, it is okay to imagine that it is on the surface of the mirror, but for mathematical purposes, it behaves as if it is exactly the same distance deep inside the mirror. It's also true motion-wise. If this were to move, this also moves. If this moves 1 centimeter, that also moves 1 centimeter. And then you can, just for thought purposes, you can ask, if this moves 1 centimeter, how long afterwards does it move? Right. So let's say, so it could be an extra credit, right? Think about it. So extra credit. Is there a delay in the motion? Is there a delay in the response of the image? You can ask the same thing and for your image also, right? When you lift your hand, after how long does your image lift your hand? Is that instantaneous or not? Most of the time when we are looking at it, it looks instantaneous because speed of light is very large. But imagine a situation where that distance is really large enough, then by the time you lift and put down your hand, after how long does that happen? Remember, everything has to happen, or you cannot pass information faster than speed of light. But we are doing statics, so this is much simpler. So most of the dramatic cases are not there, but still it is interesting enough. So now we said that we remove the conductor and we have an image charge. And also remember that we put V equal to 0, right? So phi is equal to 0, right? Inside the conductor if you want. And this is Z equal to 0. That's a Z plane. So that is Z axis. So we said if you're interested in the electric potential, we said at an arbitrary point x, y, z. So this is your origin at an arbitrary point x, y, z, which is R if you want. That's 0, 0, 0. And the position of the charge is 0, 0, A, right? Since it is on the x-axis. So if you want, this is x, y, z. We said is equal to 0 if z is less than 0. That has to be true because of the boundary condition. Even though there are images in all the things, inside phi is 0. It could be a constant also, but we set it to 0. We have a choice. It's like earthing the conductor, like whatever you do in electrical engineering, if you want any electrical circuit. But on the right-hand side, it behaves like there are two charges. There is no conductor, there's an image charge. So it is Q over 4 pi epsilon naught. That's a positive charge. And the potential due to that is given by the distance between these two the observation point and this charge. So that's x squared plus y squared plus z minus a the whole square. That's your potential due to the positive charge, but there is one more charge, there's an image charge, so that's minus q over 4 pi epsilon naught. And this is 1 over square plus y square plus z plus a the whole square. And that's the situation if z was greater than okay, that's electric potential. What about electric field? Or before we proceed on to that, let us ask what happens to the electric potential if you're right on the boundary and it is phi equal to 0 there, but what about slightly out there? How does the potential, is the potential continuous on the boundary or not? So let's calculate it slightly inside the conductor and slightly outside the conductor. So that's phi of x, y, we keep it arbitrary, and z, we say is 0 minus delta. If you're slightly inside the conductor, since z is less than, or it's inside the conductor, z is less than 0, that's 0 immediately, right? That's because that's this value. That's immediate. What about if it is outside, slightly outside, it's 0 plus delta. You're not going very far it could be this value. But if you're very close, so z is 0, so you pretty much put z equal to 0. So if you put z equal to 0, that's a square. If you put z equal to 0, that's also a square. But these two become the same. Right? And that's the case. So it is indeed 0. So it is continuous. Right? So electric potential is continuous across. It's continuous across the interface. Let's do the same thing for the electric field. And remember how will the electric field look like? So it is pretty much exactly like a positive and negative charge. So you have positive charge here and negative charge in here. The electric field inside the conductor is 0, so no questions asked. So this is 0, so E equal to 0. But outside, this behaves like there is a negative charge, so it, lines of force try to go like this. It tries to finish it, but it's 0 right there. And it's correct. That's all. The positive and negative, if there was a negative charge, this will all go. The electric field lines actually end on the conductor. That means to say that there must be negative charges there, right? So that's what we said, that it'll pull negative charges there. So there will be negative charges in here. And in fact, there will be more negative charges closer. And so there's a surface charge on that conductor. So that's good, but let's calculate this electric field. So this is how we expect it to be. So let's calculate the electric field. And electric field can be calculated if you know the potential. We just take the gradient of the potential. So electric field is equal to negative gradient of the electric potential. Take the gradient of that, and that's equal to, it is 0 if z is less than 0, no doubt about that. Right? So it's 0, or if you take a differentiation, that's 0 again. If I take the gradient of this quantity for z greater than 0, remember that what is gradient of 1 over r? The electric field, correct? So let's put a negative also. So that's r hat over r square. In fact, if it was displaced a little, r minus r prime, you just displace this also the same amount. So it is good to write it as r cubed. So it's r minus r prime over r minus r prime cube. This is the same as r over r cube. So it's the same thing. If you move it, then it's just displaced. So it's the vector displacement between the source and the observation point divided by the cube of that. So the displacement is from here to here. So we can immediately write this down, correct? So it is q over, so let me write the I hat first. So it is q over 4 pi epsilon naught times x. So this is x over x squared plus y squared plus z minus a the whole square, and that's 3 by 2. But that is the x component, and then there is plus j component. So this is, I'm just doing this. I'll come back and do this on the right hand side. So this is q over 4 pi epsilon naught. So that is y over and plus k hat is q over 4 pi epsilon naught. And this time it is z minus a. Z minus a divided by square plus y square plus z minus a square. Again, this is xi, this is r minus r prime, right? R minus r prime, x minus 0, y minus 0, z minus a. So that's all. And then the cube of that. Do the same thing for the other potential. So that's minus I hat. That's q over 4 pi epsilon naught. This goes all the way. Okay. And this is also x. So we're x squared plus y squared plus z plus a the whole square. Notice they do not cancel. Right? Numerator is the same, but the denominator is not the same. So they do not cancel. It's minus j hat. And minus k hat. Looks like a little, well, it's like a big expression, but it's mostly if because we've expanded it in the compound. But that's the explicit expression for the electric field. Again, it is 0 when z is greater than 0. And this whole thing is for z greater than 0, and that was for z less than 0. So, okay, that's good. Again, we ask the same question. What can we say about the electric field? It seems like when I draw this, because of the symmetry of the two charges, because it is exactly oppositely charged, they should be tangential at that point, right? They will go and come back here. So it seems like they should come and hit normal. Like intuitively speaking, this all should be normal, right? Because you have negative charge, positively charged, they're symmetric. So they should be exactly at the center. They should be the maximum value, right? So that's what would expect. So what that means is that electric field will be in this direction. That means it is in the negative z direction. That's what you expect intuitively. Let's see what happens right on the boundary. So the electric field at x comma y, an arbitrary x and y, but slightly inside the conductor. That's because of this value, it is just 0. It is 0, right, slightly inside the conductor, or for that matter, anywhere inside the conductor. What about electric field right outside the conductor, slightly outside, very close to the conductor, slightly outside. And then you notice that, okay, I have put z equal to 0. When I put z equal to 0 here, the denominator becomes the same, right? And x cancels out, the numerator cancels out. So it is 0 in the I hat direction. Same thing happens for y component. The denominator becomes the same, numerator is already the same, so that cancels out. That's plus 0 j hat. But the z component, now notice, the denominator becomes the same when you put z equal to 0. The numerator is not the same. Z cancels out. There's a z here, there's a z here with a negative sign that cancels out. But this is a minus a, and this, when you subtract it, that is also a minus a. So the z component is, first of all, it's negative. So it is minus k hat. And it is q over 4 pi epsilon naught. And it is 2 times a divided by x squared plus y squared, and z is set to 0, so that's a squared. Let me write that as 2aq. Is that a familiar quantity? Dipole, electric field due to a dipole. This is the dipole moment that shows up there. Very good. So as a dipole moment, and it is true, right? If there's a positive charge, negative charge, that behaves like a dipole moment. So the electric field is that of a dipole moment. Very good, right? And that's the, and notice this is in the negative direction. That means it's tangential, and it is having only a z component in there. This also seems to suggest that whatever the structure is here, I can actually, instead of saying that it is 0 for z less than 0, and it is something, it's something for z greater than 0, I can write the electric field as, electric field can be written as, remember the Heaviside step function, that's theta of z. Remember your Heaviside step function is 1 if z was greater than 0, it is 0 if z is less than 0. Okay. So the step function looks like this. It's 0 everywhere and 1 for z greater than 0. So it's z equal to 0. And I need to put whatever is the quantity when z is greater than 0, but that's electric field itself. So this whole thing, I will call it c, which is a function of x, y, and z. So this is electric field at point R. In general, instead of giving this in two pieces, where c of R is equal to E of R for z greater than 0. Right? That's just this whole value in there. What's the advantage of that? Let's see. Let's proceed, and I'll see what we can do further. Any questions at this stage? This should be very straightforward. Like that's the advantage of this method of images. Intuitively, there's a lot of clarity in there. We just need two positive, two charges. Okay, so So we have electric field given by this. Let's actually remember that Gauss's law tells us that the divergence of the electric field, in fact, divergence of epsilon naught times the electric field, is equal to, what is it equal to?
Charge density.
The charge density, right? So this is charge density. Charge density of what?
The enclosed volume.
At that point. Usually if you're talking about a volume, yes, but this is a local statement at point R, right? So if this is the electric field we know everywhere in space, where are the charges sitting? Intuitively again, I expect there to be an charge here, and seems like there are a lot of negative charges. So this should be equal to 0, probably everywhere, except on the surface or on the charge itself. So intuitively, we expect, intuitively, it's equal to 0 everywhere except at z equal to 0 and at 0. So z equal to 0 is because it is with the surface of the conductor, and there is also a charge at 0, 0, A, right? So that's the expectation. So let's see what happens. So let's evaluate that. So let's calculate gradient, or sorry, divergence of epsilon naught times the electric field. Before we proceed, we see that, oh, that's equal to a step function times something. So this is divergence of the step function, and there is the function C, right, or the electric field C. It's pretty much the electric field itself, but we wrote it as C so that it is differentiated on the left. Right. Whenever you have to take a derivative, it distributes, but this is not a vector. So since this is not a vector, this dot product is on C, but can act on this. So this is epsilon naught times, when it acts on this, it is Z dotted with C R, and I can have plus epsilon naught theta of Z times the divergence of C. Is that clear? That should be very clear. Any questions? What is the gradient of the step function? Delta function, and its direction will be z hat, right? When you take the derivative with x and y, there is no function, only with z hat. So gradient of the step function is just, since there is only z dependence, is d by dz of the step function, and that's equal to z hat times the delta function at z equal to 0. So that's equal to delta function, delta of z, and epsilon naught times z hat dotted with c, right? But now, since the delta function survives only on at z equal to 0, so I don't have to worry about everything else. So this is x, y, this is arbitrary, but z is 0, right? This is decided by the delta function. Why is this 0? Because delta function is 0. Everywhere else, this won't contribute, you know. and it is only the z component that survives. That's also, so when you take the dot product, it's only the z component that survives. And plus del dot with C, this is like C is the electric field due to 2 point charges. Right? So this is epsilon naught times, or so this is theta of Z. Right? Since this is the same electric field times epsilon naught, so I can say that this will be the charge density due to plus Q, right? And plus charge density due to negative Q. Is that clear? I mean, I've written it symbolically. Like when this acts on this whole piece here, the electric field due to a point charge at minus A, it will give me a delta function at that point. Right? So this will be equal to Q, or yeah, Q times delta Q of xi plus yj plus z. There's a positive charge, so that's z minus a k. Whenever this is equal to 0, that's when this goes to 0. And the other one is minus of q times delta function of xi plus yj, observation for the place where this goes to 0, plus z plus a k. That means the position, there is a charge at 0, 0, minus a, 0, 0, plus. But the step function does not allow this to survive. This is there, but the step function is 0 to begin with. So first you take the step, evaluate the first function, step function, and then evaluate the delta function. This does not contribute. This does not contribute, does not contribute. Because theta of z is equal to 0 when that's equal to 0. So there's only one piece in there. What about this? This can be interpreted as the charge density. So there are two charges. So we interpret so we read out, right? Read out charge density on the surface of conductor as this quantity. So let me rewrite this. Electric field is interpreted as delta of z times sigma of x, y, 0. That's a charge density on the surface, plus q times delta function of x of, so there's r and minus r of plus q. The second one does not contribute because this is cancelled by the step function. So that's an interpretation there. But the main idea is that we want to read out this charge density. And notice how easy it was. We didn't have to actually do any integrations just by differentiating the electric field. At the boundary of the conductor, the normal component of the electric field actually tells you what the charge density on the conductor is. And that's true anywhere, anytime on the conductor. Like we have done it for a parallel plate, anywhere. Any shape of the conductor, the normal, first of all, electric field always will be normal to the conductor, and its divergence there immediately gives you the charge density. It's x, y, and this is 0. And that's equal to the Z component of the electric field at 0, but that's exactly this, correct? That's exactly this. We already got that. We were actually, no, right? Am I correct? Yeah, Z component of the electric field is just this. So I take out the vector part is gone, and whatever is left is what it is. And notice that it is negatively charged. So it is 2AQ. That is 1 over minus 1 over 4 pi, and there's 2 times A times Q over x squared plus y squared plus A squared over 3 by 2. Okay. And it seems roughly there is a, if you plot this actually, so this is your conductor, right? So if you were to plot this, so that's your conductor, that's your positive charge. It is maximum when x and y is 0. There will be a maximum here, and then it will decay off. For large x and y, this goes to 0, right? So this is like this. So where I have drawn on this side, this is sigma. Because that's your xy, remember, so that's your z-axis. On the z-axis, so there's a plate here, and the charge density, there's a lot of charge along the axis of the z, but as you go on the far end of the plates, it decays off. And in fact, it goes to 0 very far away because at that point it's a nice question to ask, what will be the total charge on the plate? If I add up all those charge density, how much will it be equal to? Will it pull, like since it has a choice to pull, it's an infinite reservoir, will it pull a lot of them, or is there a limit how much it will pull? So it's a good thing to find out. So we just have to integrate, right? If we integrate this whole thing, we know exactly how much it is. So let's do that, right? So it seems like it might be doable. Let's do that. So total charge, so Q total, right, so this is total induced charge on the plate. That will be equal to integrate minus infinity to plus infinity dx, and then you do minus infinity to plus infinity dy, and this is sigma x y 0. Right? That's your induced charge density. This is symmetric in x and y, so immediately switch over to polar coordinates. That's 0 to infinity r dr, or rho d rho, right? Like rho d rho. And that's 0 to infinity d phi. And we have, I put a minus sign in front. Let me also pull out the factor, minus 2aq over 4 pi. And this is 1 over x squared plus y squared is rho squared plus a squared. 3 by 2.
Should the pi integral go to 2 pi?
Oh, 0 to 2 pi. Thank you. That's 0 to 2 pi. Thank you. There is no phi dependence in that. That's immediate. So that brings you at 2 pi. So that's minus 2aq over 4 pi times 2 pi. And an integral 0 infinity rho d rho over rho squared plus a squared 3 by 2. So 2 pi, so all this cancels out. Right? So there's a times q remaining. A good substitution probably is rho is equal to a tangent theta. And then d rho is equal to a secant square theta. and a d theta. So that's equal to minus a times q. When rho is equal to 0, tangent theta is also 0. When rho is equal to infinity, tangent goes to pi by 2. There is a rho and d rho. D rho is a. Am I doing this correct?
To replace row also.
Yeah, to replace the rho also. Yeah, that's correct. Good. So this is a, and then a square tangent theta and secant square theta d theta. I think it's correct, probably. Divided by, and then there is this is a cube, right? There's an a cube, and what is it? 1 plus tangent square, which is secant square. So this is secant cube apparently. Hopefully, what's up? Dimensionally, it seems okay because all the distances cancel out. Right? And what is this? 2 secant square cancels out. Oh yeah, that's sine theta, right? So it's equal to minus q 0 to pi by 2 times sine theta, I guess. D theta. And why am I getting this? So sine theta integral is plus, right? So minus q, and no, sine theta integral of sine theta is minus cosine theta. And you evaluate it from pi by 2 to 0, and that's equal to minus q times 0, and this is plus 1, okay? So it's plus 1. So apparently, exactly minus q is pulled on the chart, right? From the infinite reservoir, it had a choice to take as much as it wants, but it pulls out exactly minus q, the image charge on that conductor, which probably is not immediately obvious, but maybe not very. One could argue that using other quantities also. Okay, so that now we know the surface charge density, so it's very clear how much charge is distributed, everything. But next, we have to find out what about the force, right? Now there are two ways of finding the force. Now that we know how much charge density is there, we can ask what is the force between the conductor and the charge? And we can also ask, is it the same as the image charge? So does that reproduce a force? But those things we will do. We'll do on Friday. So we'll calculate the force using two methods, using explicit method of the charge and the induced charge, and see if the image charge reproduces that or not. And we'll do that analysis on Friday. Thank you.